Hi, today we are going to start our next section 6.3 Annihilating Polynomials. Okay, now let's look at the definition. Let V be a vector space over the field F. Okay, suppose T is a linear operator on V. If P is a polynomial over F, then P of T is again a linear operator on V. Okay, so if you suppose our p of x is like this. Some p of x is equal to some 2x plus 3x square. Now what is our p of t? P of t is 2t plus 3t square. Okay. So what is t? T is a linear operator on V. T is a map from V to V. So what is t square? T square is t composition t, which is again a linear operator on V. Okay, so 2t plus uh, 3t square. This is again all these are linear maps. Suppose f and g are function, though f plus g is again a function. Therefore 2t plus 3t square is again a linear operator from V to V. Okay. Okay, that's okay, if p is any polynomial over f, then p of t is again a linear operator on V. Now we are defining some operations, addition and multiplication. If q is any other polynomial over f, then we define addition as p plus q of t is equal to p of t plus q of t, and multiplication as pq of t is equal to pt into qt. Okay, we are defining like this. Okay, now moving to the definition, let t be a linear operator on V. Then a polynomial p of x is called an annihilating polynomial for t if this is called an annihilating polynomial for t if p of t equal to 0. That is 0 means 0 linear operator on V. Okay, then we call the polynomial p of x as a annihilating polynomial for t. Okay. Now the collection of all polynomials which annihilate t is an ideal in the polynomial algebra. Now what is mean by an ideal? By definition, what is ideal? Just to recall the definition of ideal. We have by the definition of ideal, an ideal in f of x. What is an ideal? Suppose f of x is an ideal in m of f of x is an ideal if f g belongs to m whenever f belongs to f of x and g belongs to m. This is the definition of ideal. Okay. Now by our definition in field, ideal means let R be our ring and N is a non-empty subring of R, then N is called an ideal if An subset of N and N be subset of N. Okay. So what is An actually? An means left coset is contained in N. Okay. That's what here also. Here A belongs to R, here F belongs to F. Here R is F of X, and for N here we have M. Okay, therefore Fg belongs to M means actually A N, because A means A belongs to R. Some A, but what's the meaning of An subset of N? An subset of N means A into X belongs to N. Okay, for x belongs to n, ax belongs to n. Okay, no need to worry about this definition, just recall this definition only. Okay, so here what we have to prove, we have to prove the set of all polynomial which annihilate t is an ideal. Okay, so let n be the collection of all polynomial which annihilate t. That is, set of all p of x belongs to f of x such that p of t equal to 0. And we have to prove that this is an ideal. First, we prove this set is non-empty. Okay. So for this, let T be a linear operator on a n-dimensional space V and consider the operator I, T, T square, T cube, etc. T raised to n square. How many linear operators are the total number is n square and plus this I. That means n square plus 1 linear operators in LVV. Now what about dimension of LVV is n square. So these one I, T, T square, etc. T raised to n square are n square plus 1 linear operators. That means this set is linearly dependent because dimension is n square. Any set containing more than n square vectors must be linearly dependent. Therefore, this is a collection of all n square plus 1 vectors. Therefore, this set is linearly dependent. Linearly dependent means there exists scalar C1, C0, C1, etc. Cn square, not all zero such that this linear combination is equal to 0. Okay. Therefore, if you consider any p of x such that p of x equal to c naught plus etc. plus cn square x raised to n square, then p of x is clearly non-zero because these ci's are not all zeros. Okay. Therefore, p of x is a non-zero polynomial having degree n square. Okay. N square or less, because if cn square is equal to 0, then degree of this p of x must be strictly less than n square. But clearly p of t equal to 0. Therefore, this p of x is belongs to n. This implies n is non-empty. Okay. If you take any linear operator, then if you consider this polynomial, okay, then that p of x must belongs to n. Now, to prove n is an ideal, we have to prove fg belongs to n whenever f is in f of x and g is in n. So suppose f belongs to f of x and g belongs to n. G belongs to n means g of t equals 0 by the definition of n. Okay, so what is f of g of t? F into g of t. By definition, this is f of t into g of t. But g of t is equal to 0. Therefore, f of t into 0, which is equal to 0. Therefore, fg of t equal to 0. This implies fg belongs to n. Okay, therefore, the set of all polynomials, the set of all collection of all polynomial which annihilate t is an ideal in f of x. Now we have one result. There is by theorem 7, 132. And the theorem, the statement is, if f is a field, then m is any ideal, non-zero ideal in f of x, then there exists a unique monic polynomial d. D is not a constant, d is a unique monic polynomial. What is the meaning of monic polynomial? The highest coefficient of the highest power is 1. That is some x raised to n plus some an minus 1, x raised to n minus 1 plus etc. form. Okay, coefficient of highest power is 1. Then such a polynomial is called monic polynomial. Then this theorem says that then there is a unique monic polynomial d in f of x such that m is the principal ideal generated by d. M is the principal ideal generated by d. What is the meaning of that? M is the principal ideal generated by d. If f is any polynomial in m, then f you can write some d into g of x. That means f of x you can write as a multiple of d. You must remember d is not a constant, d is a unique monic polynomial and f of x must be a multiple of d. M is a principal ideal generated by d means yeah, every element in M is a multiple of d. Okay, just remember this. M is a principal ideal generated by d, or M is a principal ideal generated by d. You can write d is equal to some r of x. Then actually M is equal to ideal generated by r of x. This is the notation. Okay, that means every element in M you can write as a multiple of this d equal to r of x. That means if f of x belongs to M, then f of x you can write as d into some g of x, or as d equal to r of x, this you can write as r of x into g of x. Okay, so here we have annihilating set. N is a ideal in the polynomial algebra. That means n is an ideal in f of x. Therefore, The collection of all polynomials which annihilate T has also a monic polynomial as generator. Okay. This theorem says that if f is a field and m is a non-zero ideal in f of x, then m is a principal ideal generated by some unique monic polynomial D. Here n and the collection of all a polynomial which annihilate T is an ideal in f of x. Therefore, by this result, by this remark, n also has a unique monic polynomial D as a generator. Okay. Now, the next definition of minimal polynomial. Let T be a linear operator on a finite dimensional vector space V over the field F. Then the minimal polynomial for T is the unique monic generator of the ideal of all polynomials over F which annihilate T. Okay, ideal of all polynomials which annihilate T. The collection of all polynomials which annihilate T is an ideal in the polynomial algebra. As f of x is f is a field, f of x, every ideal in f of x is a principal ideal. Therefore, this our n, the set of all polynomial which annihilate T, is also a principal ideal. That means it has a generator. That generator is called minimal polynomial for T. So, minimal polynomial for T must be a unique monic polynomial. Okay, it's a monic polynomial. Okay. So, and it is a that minimal polynomial is also a generator for the ideal of all polynomial which annihilate T. What is the meaning of that? Suppose P of x is our minimal polynomial and n is the ideal of our polynomial which annihilate T. That means if you take any sum q of t, q of x belongs to n, then q of t such that q of t equal to 0, then this q of x must be a multiple of p. That is q of x you can write as some p of x into r of x. Every polynomial which annihilate t annihilate T is a multiple of P of x. Okay. As P of x is the minimal polynomial, P of x is a generator for the ideal of polynomial which annihilate T. P of T must be equal to 0. Okay. Now note 2. The minimal polynomial P for a linear operator T is uniquely determined by the following three properties. P is a monic polynomial. Okay. P of T must be equal to 0. No polynomial over f which annihilate T has smaller degree than P has, because every polynomial which annihilate T, that is q of x, such that q of t equal to 0 implies this q of x is a multiple of P of x, some P of x into R of x. Now what about degree of q of x? Clearly that must be a degree greater than or equal to degree of P of x. Therefore, no polynomial over f which annihilate T has smaller degree than P has. Okay. Now next, if A is an n by n matrix over F, then we define the minimal polynomial for A as the unique monic generator of the ideal of all polynomial over F which annihilate A. Same as the definition of a linear operator. Which annihilate A means set of all polynomial which annihilate A means set of all P of x such that P of A equal to 0. Now there is another note, last note. If the operator T is represented in some ordered basis by a matrix A, then T and A have same minimal polynomial. That means we have to prove that minimal polynomial for T and minimal polynomial for A are same. Now moving to the proof. Let P of x equal to C0 plus C1x plus C2x square plus etc. Cn x raised to n be any polynomial. Okay. Now what is P of t? Just replace x by t. Suppose given matrix of t related to b equal to A. Now what is P of A? P of A is C0 I plus C1a plus etc. plus Cn a raised to n. Suppose P of t equal to 0, then clearly P of A equal to 0. Also if P of A equal to 0, then P of t equal to 0. How? Suppose matrix of T related to some ordered basis B by A. Okay, and suppose t is a suppose some c naught t plus c1 t square is equal to 0. Okay, now what about this? This is a zero linear operator. This is equal to 0. Now consider matrix of t related to this linear transformation. What we have? We have C naught into matrix of t related to b plus c1 into matrix of t square related to 0. That is c naught plus a plus c1. What about matrix of t square related? This is a square is equal to 0. This implies this equal to 0 implies corresponding. Suppose some p of a p of t equal to 0. This implies p of a equal to 0 matrix. This is a 0 operator. This is a 0 matrix. This right hand side is a 0 matrix. And here right hand side is a 0 operator. Okay. So we have to prove minimal polynomial are same for a and t. Assume p1 is the minimal polynomial for t and p2 is the minimal polynomial for a. Since p1 is a minimal polynomial for t, p1t equal to 0. p1t equal to 0 means p1a equal to 0. But p2 is a minimal polynomial for a. Therefore, p2 of x is the unique monic generator of the collection of all polynomial which annihilate a. This implies here p1 of a equal to 0. That means p1 of x is equal to a multiple of p2. p2x is the generator. P2 is the minimal polynomial for A. P1 of A equal to 0. Therefore, any polynomial with this equal to 0 means P2x is the minimal polynomial. That means P2x is the generator. That means P1 of x you can write as G1x into P2 of x. Therefore, degree of P2 of x is clearly less than or equal to degree of P1x because P1 of x equal to G1 of x into P2 of x. Okay, some G1 of x is another polynomial. Therefore, degree of P2 of x is clearly less than or equal to degree of P1 of x. Hope it is clear because P2 we, as P1 of t equal to 0 implies P1 of a equal to 0. Now P2 is the minimal polynomial for a. That means if some q of x is any polynomial such that q of a equal to 0, then q of x you can write some g of x into q of x. This is the definition of a generator. Okay, sorry, q of x you can write as g of x into p2 of x. Okay, but here for q of x we have p1. Therefore p1 of x you can write as some g1 of x into p2 of x. Okay. Now similarly you can apply this. P2 is a minimal polynomial for a. Therefore P2a equal to 0. This implies P2t equal to 0. Now P1 is the minimal polynomial for t. Therefore it is the generator for the annihilating polynomial. This is P2 is an annihilating polynomial for t. Therefore P2 of you can write as G2 of x into P1 of x. Therefore from this degree of P1 of x is less than or equal to degree of P2 of x. Now from 2 and 3 we get from 2 and 3. This is degree of P2 of x less than or equal to degree of P1x. Here degree of P1 of x less than or equal to degree of P. From 1, 2 and 3 we get degree of P1 of x is equal to degree of P2 of x. We have P1 of x equal to this one and P2 of x equal to this one. Degree of P1 of x equal to degree of P2 x. Now what about this one? G1 of x must be a constant. Degree of P2x equal to degree of P1. That means G2 of x is also a constant. This implies G1 and G2 are constant. Now P1 of x is equal to G1 of x into P2 of x. This one. For P2 of x you apply this one. Therefore P1 of x you can write like this. Okay. So from this what we get G1 of x into G2 of x equal to 1. G2 of x equal to, if G2 of x equal to C, then G1 of x equal to 1 by C. Therefore P2 of x you can write as C into P1 of x. But P1 and P2 are monic polynomial. C is a constant. Suppose P1 of x is a monic polynomial. Suppose C is equal to some 3. P1 of x is a monic polynomial means some x raised to 4 plus 5x square, etc. Okay, monic polynomial means degree of the coefficient of the highest power must be 1. Now what about CP1x? That means 3x raised to 4 plus 5x raised 5 into 350. Okay. x raised to square plus etc. this side. But this is also a monic polynomial. That means c must, that means p2 of x is some x raised to 4 plus etc. But here these coefficients are not equal. So this is possible only if c equal to 1. Therefore, p1 of x equal to p2 of x. Therefore, t and a have same minimal polynomial. Okay, that's all for today's class.